we're going to look at an effect that's called the Hall effect. And this is the first experimental evidence for what the sign of charge carriers in a conductor is. And Hall effect is used to measure parameters for different conductors. So it's the number density of charge carriers, and how you can get at what goes into the resistivity of a material. So in the Hall effect, we're going to have a sample of metal, a conductor here in orange. It has a width W. There's a magnetic field going into the plane of the page, and we have a current that's going up the page. Now we're going to consider the two possible cases of this current I. The first case we'll look at is it is conventional current. So that's meaning positive charge carriers. So if the conventional current going up the page is made out of positive charge carriers, then the magnetic force in the conductor is going to push positive charges to the left, because that would be V cross B is a magnetic force to the left. So this side of the conductor, the left side, will build up a positive charge, and there would be an absence of positive charges on the right side. So those would be negative. So the Hall voltage measured left to right would be a positive number if it was conventional current. All right, if instead that current I was a physical current with negative charge carriers, then positive charge carriers going up the plane of the page is the same current effect as negative charge carriers going down the page. Okay, so now we would have negative charge carriers moving down the page. So V cross B is going to point to the right side, right? But the magnetic force is in the opposite direction on negative charge carriers. So negative charge carriers would get pushed to the left, and we would have an absence of negative charge carriers on the right side. So the Hall voltage measured left to right would be negative. The same magnitude, but opposite orientation. And this is how Hall was able to determine that it was actually negative charge carriers in a conductor that are free to move about. Now, these charges are going to build up until the electric field cancels out the magnetic field. The Coulomb force cancels out the magnetic force. And that's going to give us a condition on the electric field inside the conductor. So the electric field is going to be the Hall potential, so the change in voltage over the width, and that lets us measure the speed of the charge carriers and magnetic field strength. So the Hall effect lets us measure what the drift speed of the charge carriers actually is. So in a Hall effect experiment, you would measure W, the width of the conducting sample. You would know the magnetic field you're applying. You read off what the Hall voltage is, and that gives you a measurement of the drift speed and the characteristics of that particular conductor.